I will get going. I don't want to shout, because if I shout, then things get really crazy in the video room next door. We're going to get this audio figured out soon. Again, my name's Jason. That's my email address up there, so you can read it. I do have office hours. Had one today at 3. Check, check. Okay, so that's good. And it's over in room 129, the same place where Brian was. I'm going to try in the future to start these lectures at 5:10, and then I'm going to end at 6. So that's the plan. So I get completely wired for sound here. I'm emitting radio waves in all different directions. Okay, and I'm going to, after this at 6, I'll just kind of go out in the hall, clear the room for the next professor, but I'll wait around there in case anybody has any questions from either room. So if you're over there in the video overflow room, you can see me out there as well in actual person. While people are getting seated, I'm going to talk about some stuff that is not physics related. I'm going to introduce myself a little bit by telling you 5 random facts about me that are not on any test. Okay. Number 1, I ride my bike to work. Rode my bike this morning. I'm going to be riding my bike home with a light tonight. Number 2, I have 6 kids. So while I was a grad student, two daughters who are now, actually one's a grad student at Guelph, she's 23, and my younger one is just finishing up her 4th year at University of Waterloo doing psychology and sociology. I also have 2 stepsons who are in Humberside High School. And I have 2 little ones, my son and my daughter, who are 4 and 7. I once discovered a star when I was an undergraduate here at U of T. In my 4th year, I was doing a research project at the David Dunlap Observatory, which is a 2-meter class telescope in Richmond Hill. It was still operating back then, and so I was doing a radial velocity survey, which means I was looking at Doppler shifts in light from many nearby stars, and I was going through a catalog of nearby stars and making precise measurements of the radial velocity. One star, Gliese 372, I looked at it one night. I decided to get a better measurement by looking at it again to kind of average my uncertainties down, and it was way off by like 40 kilometers per second from the previous night, and so I obviously thought I'd got the wrong star. I must have not looked through properly. And the 3rd time it was doing something else, and so what I realized is that it wasn't me, it was the star. The star was moving, and so what that usually means is that it's caught in an orbit with another unseen companion star that's fainter, and so I ended up writing a paper on that and discovered, I guess, that companion, Gliese 372b. So that's that's actually one of the things I said to my wife on our first date when I was trying to impress her, and it worked. So, and speaking of her, I have some family through my wife in Pakistan. So some uncles and aunts, and I've been over there visiting, planning to go back, and it's an interesting place. And my PhD was entitled Faint End of the Stellar Luminosity Function. It's a book. I was looking at nearby stars, looking at the sun and its companions, other stars that formed in the same time. Seat right up here, seat right over here, whole bunch of seats over on this side. Please come on in, you're welcome. Lots of seats, empty seats all over the place. No more video overflow room. Welcome. Okay. So, I have posted a homework number 7, which is due on Friday, November 2nd. I have also posted an optional item on this Mastering Physics called Chapter 7 Videos Optional. And you can check it out. There's actually a picture of the author of the textbook. I don't know if Pius is still around, but I'd like to dim the lights at the front somehow. I don't know how to do that. Do you know how to make this light go off, but those lights stay on? One of those switches. So this is actually the same author, and she's actually rolling Hot Wheels cars off at different angles and reproducing one of the experiments that's actually in the textbook, but in a video form, so it's kind of fun. This is who I call Buzzcut Guy. He does all kinds of crazy things, and he's in a lot of different Pearson videos. And what he does is he holds a bowling ball up to his chin. It's hanging on a big string. and then he lets it go, and it swings back and forth, swings way out, and then comes back. But it comes to the same height, just below his chin, and since he released it from rest with zero kinetic energy, when it comes back to the same position, the kinetic energy goes to zero again and doesn't knock his teeth out, and that's fun to watch. He looks very scared, though, while he's doing it. So he's got to have more trust in the idea of conservation of energy, I think. So there's also a couple of sort of, I guess, Khan Academy style videos where they're going through solving problems using the concept of conservation of energy and crossing things out and coming up with solutions. So those are kind of fun. Okay, all right. So things are settling down now. I don't know what time it is. 5:20. That's good. We're actually on schedule here. So, what's the big idea? So, we are moving on to chapter 7. So actually, if I hit the switch button, what's it going to do? Oh, is that here? Right there. Let's see if my dock cam is on. Okay, so that's the book. This is sort of where you are. Let's put the zoom in a little bit. So we have done 1 to 6. We're done that. We're done chapter 6. We're now on chapter 7 on conservation of energy. There is stuff like, torque coming up. I'm going to finish all the way up to the end of chapter 11 on mechanical waves. So we get into this vibration wave section. We're going to finish up that. And then that'll bring us to the final exam, which is on all of this stuff, chapters 1 through 11. And then there's another course that starts up in January called Physics 132 you might be interested in, and that starts in with electricity and magnetism, gets into optics, which is a lot of fun, and ends up with special relativity and E equals mc squared and that kind of stuff. So now, I hit the switch button. There we go. So on chapter 7, it's similar to chapter 6 in that it starts with a conservation idea. And Brian introduced this idea there was 10 oranges in a bag, and you give 2 to a friend, and how many oranges are left? Remember that one? And it's 10 minus 2. It's 8. But it could be 10, because it depends how you define the system. So if the system is bag, well, then what you've done is some oranges have left the system. Okay, so you can add oranges to the system by putting them in the bag or take them out. Or you could define the system to be the entire universe, in which case you have this conservation law called conservation of oranges. Unless you plant an orange tree in your backyard, which then somehow creates oranges out of nothing. So it's not actually true that there's a conservation of oranges law in physics, as you know. But there is conservation of momentum, and there's conservation of energy. And so the idea is that some things can stay the same even while a bunch of other things are changing. So, example, let's say conservation of mass. If we have a dish and we know its mass, and then we smash it on the floor, but we gather up all the pieces and measure their mass, we expect the mass of all those pieces to equal the mass of the original dish. If it's less, then we would assume naturally that we've missed a piece and then it's flown under the fridge or something like that. If it's more, I don't know what we would we would get a little confused, right? So and maybe there had been a previous dish that got broken and we picked up that somehow. So we intrinsically believe somehow that by throwing a dish on the ground, you don't create or destroy dish. Like it still is. You don't create or destroy mass. And then similarly, in physics, we do reasoning based on this idea of conservation of momentum and conservation of energy to solve problems. So what is energy? Energy is a property that you can measure, like age or height or mass. So these are numbers, right? I have some age, it's 46. I have some height, 1.8 meters, something like that. I have a mass. So energy is a property of an object. And there are different types of energy. So there's total energy, but that total energy is made up of a bunch of different parts of the total energy. Some of them, they're all scalars, meaning that they don't have direction, but some of them can be positive only, like kinetic energy, the energy of motion, and some can be positive or negative. So there's two kinds of scalars in the world. There's scalars that are always positive, like I guess mass is an example of that, and scalars that can be positive or negative, like the temperature. You can go minus on the Celsius scale, right? So this gravitational potential energy, which this textbook uses U sub g, is an example of a scalar property which could be positive or negative, depending if you're above or below the kind of 0 point. And we'll give some examples of that. Energy has units. The units happen to be joules. And I've already lost my pen. Oh, there it is. And energy is relative. So if something is moving like a car on the road, you would say it has kinetic energy. But if you're in the car right beside that car driving along at the same speed and same direction, then you would say that that car is at rest relative to you. And the whole world is flying by. And so in that reference frame, the moving car has 0 kinetic energy. Sort of a tricky concept. But since motion is relative, kinetic energy is also relative. And so there's just an example, something that's going fast. We're going to learn more about this next class. The equation for kinetic energy is 1/2 mv squared, where v is the speed, m is the mass of the object. Again, we'll learn more about the equation for U sub g, the potential energy, but basically it's mass times g, which is 9.8, it's that old acceleration due to gravity, times y, where y is the height. Okay, so example, if you're up on a roller coaster, your energy comes from the fact that you're way high up. And there's no motor actually on this roller coaster. What happens is as you go down, all that potential energy gets converted into kinetic as it goes down. There's also something called U sub s. So U sub g was the gravitational potential energy, and U sub s is called spring potential energy. Idea being, if you compress or stretch a spring, it also has some energy in it. And the way I like to try to remember this one is I think of a mousetrap. So please come on in. I can see, raise your hand if you have an empty seat beside you right now, please. There's a newcomer. Okay, so there's lots of seats over here. Okay, what was I going to say? A mousetrap. So imagine a mousetrap that's loaded versus a mousetrap that's not loaded. What's the difference? Could be the same name brand mousetrap, same color, same mass. So there's something different, especially if you're a mouse, right? One is safe, one is not safe, could kill you. And so it stores a bunch of energy. That's the difference. The loaded mousetrap, somebody's done some work on it, and it's holding on to all of this potential energy that can snap the mouse's neck. Sorry for the violent imagery there, but it's really true if you're a mouse. You know, spring potential energy is a real thing. Here's another form of energy we're going to talk about more today is this thermal energy or internal potential energy somehow. It comes from temperature. So this rock over here has less kind of energy per mass than this rock over here. And that's why this is high temperature, and you can even see it glowing. And it's proportional to temperature, actually. If you double the sort of absolute Kelvin temperature, you double the internal energy that's stored in an object, usually. Okay, we're going to do the dominoes next, which are over there on the floor so you can see them. You might have to do this. But this is an example of gravitational potential energy, which is stored. So potential energy means it's the potential to move, okay? So we've got all these dominoes, and again, I don't think anyone can see it. You guys can see it. There's a bunch of dominoes on the floor, and you might be able to see the biggest one at least, which is about 1 meter high, about 100 pounds. So I'm putting work into it as I push it up. So what I did is I pushed a force over some distance, and I increased its kind of height. So it's a rectangular solid. It's kind of unstable. If I bump into it, the whole thing could fall over. So it's in unstable equilibrium. A small perturbation can cause the thing to fall. And then there's a domino that's smaller than it, 1.5 times smaller, and smaller, and smaller, and smaller. And it turns out that a domino, when it tips over, can knock over another domino that's just 1.5 times bigger. So this is the idea of chain reaction. I'm going to take this pen, and I'm going to gently tap the smallest domino. And again, only the people in the front row can really appreciate this. And you can feel free to stand up if you want. Want to see? 1, 2, 3. Okay, so now that scared me. I have just destroyed the floor. Okay, so, sorry. And my own eardrums. All right, so that was a chain reaction. I put in a tiny little bit of input energy, and then there was a huge output. Where did that energy come from? Where did it come from? Why did that suddenly blow up in my face when I tapped it with a tiny little pen? Where's the energy coming from? What if I do it now? Nothing. What's the difference? Why is it different now than it was before?
It's now falling, so there's no additional mass when it falls over on another one because it's chain reaction.
It's all fallen. These are all lying down. So what's the difference between a bunch of dominoes that are lying down versus a bunch of dominoes that are standing up? This is stable equilibrium, that's true. Is there an energy difference? Yes? Yeah. Potential. This has less gravitational potential energy. And if I want to add gravitational potential energy, I have to do work in the system. I have to pick these up again and and use all that energy from the Just Right cereal I had this morning, which is converted into chemical energy in my body and goes into my muscles, and I go and pick it up. And now I've added energy to the system, and then I can knock it over again. So great. Okay. Now we are getting a little behind. So I have referred to this a couple of times, but let's define it. The most basic form of energy in the way this textbook starts off energy is work. Work is a form of energy that involves force and distance. In fact, it's force times distance. And in fact, to be more specific, the equation is work equals force times distance times the cosine of theta, where theta is the angle between the force and the displacement. So displacement means that the thing has moved. So you have an application of a force and then movement of something by that force. Okay? And we can do a couple of examples of that using my briefcase. So, example, here's my briefcase. If I apply a force to it, that's to the right, and it moves to the right, then the force of my hand on the briefcase is to the right. The displacement is to the right. So I would say, I think, that this angle here is, I guess, theta equals 0 degrees. It turns out that the cosine of 0 is 1. So you just get F equals, work. Well, I have to erase that now. The work is equal to F times the distance times 1. And it's positive. Positive work means you're adding energy to the system somehow. I am adding energy to the briefcase, and maybe it's getting faster and faster, for example. Other thing that can happen is I could be kind of carrying the briefcase upwards like this, applying an upward force, but while at the same time as just walking at a constant velocity to the right, without speeding up or slowing down. So the force, if you can believe it, is directly upwards, at right angles to the displacement. So the angle theta is what? 90 degrees. Does anybody know what the cosine of 90 degrees is? 0. You guys are on top of it. So the cosine of 90 degrees is 0, so it's 0 work. And I like to think of that as I'm not causing it to speed up or slow down. I'm applying a force. It is moving, but my force is in the wrong direction to help it move or to hinder it from moving. And so that's where we get to negative work. And this one is weird. I'm pulling it to the left, but it's moving to the right. Can you picture that? I think the only way this works is if it has some big, like initial velocity to the right, and I'm going, oh no, that briefcase is about to hit those tennis balls, and I'm pulling it to try to slow it down. Does that make sense? It's hard to picture. I'm not going to do the demo, but I'm pulling. So in that case, what's happening is that this angle is a 180. And the cosine of 180, you might not know. Does anybody know? -1. All right. That's right. It's -1. So the work is equal to negative the force times the distance. Okay. So what I want to do is go on the learning catalytics. There's a couple of things. Oh, I'm going to skip that one. I'm going to do this one. Okay. So hopefully on your computer or on your phone or whatever it is, you're now seeing a little question about this. So this is a tiny little picture of your prime minister, no, somebody with no shirt on doing a bench press, meaning you've got a bar which is pretty heavy, might weigh, for example, 200 newtons, but you're slowly pushing it upwards, slow and steady, which is hard work. So it's hard work. What is the work done by Justin on the bar? So the force of Justin on the bar is 200 newtons upwards. The displacement of the bar is 0.3 meters upwards. Unless you think about that one. Okay. I'm going to stop this one. Yeah, so that's pretty good. So a lot of people were getting 60. I think the idea there is that the force is upwards, the force of, I guess, Justin on the bar. I find it very hard to write on this thing. And then the displacement is upwards, d. And so the theta here in this case equals 0, and you just got work is equal to 200 times 0.3. And the answer is, 60 newtons times meters. And a newtons times a meter is 1 joule. So it's 60 joules. Okay. Next question is related, but different. Now, this is hard to picture, but, well, if you've ever done a bench press, the next thing you have to do is lower it down, but you don't want to just drop it, because then it's going to go crash right down into you, and it's going to really hurt a lot. So you have to actually push upward on it as you slowly lower the thing down. You picture that? To not kill yourself. So you're still pressing upwards with 200 newtons, and very slowly it comes down 0.3 meters. How much work does Justin do on the bar? 1 minute. 4, 3, 2, 1. Survey says D. So that was good. So basic idea there is that the force and the displacement are in opposite directions. Numbers are the same, but you get negative work. And then the last question in this little series, again, 1 more minute for this one, is both. So now an entire bench press is you picked up a thing, you go down 0.3 meters, and then up 0.3 meters. What's the total work that Justin does during the complete downward and upward motion? Yeah. So, Justin might argue with you, but believe it or not, in physics, we say that he did 0 work on the bar. And one of the ways I like to remember this is that the bar starts and ends in the exact same situation. He hasn't made any physical changes to the bar, like changing its height or speeding it up. It was at rest at the beginning, it's at the rest at the end, so he did 0 work. Even though it certainly causes you to sweat a lot. You're just producing heat. So this is the idea, is that when you do work on a system, you increase its total energy. So this E letter is the sum of all the energy, the kinetic plus all the potential energies that you can think of, including thermal. So the idea is that you define a system with some E initial, and now you do some external work on the system, which could be positive or negative energy that's added. And we'll be solving problems with this on Monday. Let's do a quick demo. I have a spring-loaded ball there. The spring has some spring constant K, and I'm going to launch it. And the idea is that there's 3 different positions the ball can be at. A, and it's time A, I guess, when I'm about to launch it, it's at rest. Then the spring is going to go spring, and then it's going to be B, where it's going upwards, and then C is when it reaches the top of its path. Ready? This is the motion we're going to analyze. There you go. So that was it. Imagine it's going straight up. It didn't go right back in, but it stopped momentarily at the top of the path, and that's time C. And do I have to just quickly? Let's. You've got the energy initial plus the work equals energy final. So that's the equation we're going to use. And what we're going to use is similar to the book. We're going to use these energy bar charts. So I'll show you how that looks. So the energy bar charts, so we're going to start at point A. Point A, the spring is compressed some distance. This is the equilibrium for the spring up here. And so if this distance is h min, we'll say x equals h min, then this spring has some positive potential energy. So we draw the 0 point down here, and we draw this box showing that it's got positive potential energy. The gravitational potential energy, if you start at y equals 0 here and it's negative, then this will be negative, and so you draw 0, you draw the bar being kind of below the 0 point. It's at rest, so V sub A equals 0, so the kinetic energy is 0. The work we're going to say is 0 because this is work done by some external forces, so that's not going to happen in this case. And then at point B, the spring has uncompressed. Okay, so this is sort of like a 0. And then the potential energy of gravity is y equals 0, again, 0. So what's happened is that this has sort of canceled out some of this, and it's moving. So you get a little bit. So whatever is over here, this positive minus this negative, ends up being this over here. So it's sort of a visual representation. And you can do it in terms of equations if you do like 1/2 k times, I guess, h min, sorry for the squared, plus m times g times negative h min, plus, all the zeros, 0 plus 0, equals, again, 0 plus 0, plus this kinetic, which is 1/2 m times vb squared. So you can kind of solve that out if you want, and you end up with 1/2 k h min squared minus mg h min equals 1/2 m times vb squared. So that is a useful equation that you could then use to solve, I guess, how fast it's going at step B. So, and then I guess the other thing we could do if we wanted to look at, consider time B to time C, same sort of thing, except now you're at B, where the spring is uncompressed, so that's 0. At point B, it doesn't have any gravitational potential energy because you've defined that to be the 0 point. It is moving, so there's your kinetic, no work. And then up at point C, the spring is still uncompressed because it's not attached to the spring anymore. It got released from the spring, so the spring is still at equilibrium. But it's now at some height. And it's stopped. So all that's happened here is that 1/2 mass times VB squared is equal to m times g times h max. And so that's that equation. Again, kind of useful. And what is interesting is that we've already learned ways to use like force and force diagrams and kinematics and acceleration to analyze this motion, except maybe the spring part. But certainly once it's flying, we could have done this using, we could have found this using kinematics basically. But now we have a new method which is mathematically equivalent, but it's a different kind of concept. We're conserving energy. Okay. So this is the generalized work energy principle, which comes up a lot in the textbook. But this is an idea of defining the system as being a box plus maybe the floor that it's on. And you have some hands which are not in the system. And the hand applies a force to the box and pulls it over here. So the bottom of the box and the carpet warm up. So the energy associated with both temperature and structure is called the internal energy. And you can even detect that. So we're going to try to detect that right now. This is a picture from your textbook showing results of a thermal camera. So what a thermal camera is it's using infrared waves, which are just like light waves, except that your eye is not sensitive to them because it's just slightly the wrong wavelength, slightly longer wavelength than red light, so it looks invisible. But it's very easy to grab a detector that does detect thermal. So how do I do that? I'm so glad you're here, Pius. Otherwise, there's too many gizmos here. So this is a thermal camera, and I guess if I put my hand in front of it, there's my hand. If I put this hand in front, you can see kind of my wedding ring, I guess, is a little less hot than my finger. I don't know if I can stick my face right in front of it. Hello. Okay, and also if I put my hand on the surface and then let go, do you see my handprint? Ooh. So what I'm going to do is put the bowling ball down. Whoop. Can you see the box? Kind of. Let's put it way out here, way at the edge. And now I'm going to move the box. Oh, you can't really see it. See, it's starting to warm up a little. And you can imagine if you take your two hands and rub them together, it starts to warm up, right? You feel it. And so you can sort of see that from the thermal camera as well. So the idea is I'm doing work on this box, even if it's moving at constant velocity. Meaning that as it's going along constant velocity, it's not speeding up, so I'm not changing its kinetic energy. But I'm still doing work, and where is all that energy going? It's going into the thermal energy of the table, I guess. So now I want to go back to this. We got a couple more minutes. Like I have another learning catalytics coming up, which means I'm going to need to see I'm going to need to see that. Exactly. Thank you. Okay. Are we good? So this is a weird one. And I'm going to deliver it to your phone or to your laptop. And this really was a difficult one for Con Hall this morning. So let's read it carefully. Yesterday in my office, and this actually was on a final exam, I think 2015 or something, I pushed a box, initially at rest, across the rough floor to the other side of my office where it now rests. Maybe I pushed it at constant velocity. You can imagine I just push it. It was initially at rest, finally at rest, kind of like that bench press, actually. And what we're thinking of is the work that I do on the box, the work that the friction force does on the box, and the sum of those two works, which we call the net work. Okay, so it's possible for work, either of these works to be positive or negative or zero, I guess. And that's the question. So I'm going to give you 2 minutes to think about that and discuss. And then we'll discuss. Let's see what I would say about this. And let's do a stop here. Delivery. Going once, going twice. Stop. Okay, so this is my feeling, okay? And there was some argument about this after class yesterday. That let's, for example, imagine that as I push this thing, I'm pushing with 100 newtons and it goes 2 meters in that direction. I push to the right with 100 newtons to the right and it goes 2 meters to the right. That's 100 times 2, that's 200 joules of positive work that I've done on the box to get it from here to here, okay? Now, then the question is, what's the force of friction? Well, I guess then you have to make some assumptions. Now, I think if I am pushing at a constant velocity while it's moving, then the friction force is 100 newtons, because it's at equilibrium. So for a lot of this motion, it's certainly 100 newtons. I had to give it probably, it had to be a little less than that initially, I guess, in order to get it accelerating. Or maybe I pushed a little more than 100 newtons. I'm not sure which happened there. But certainly it must have accelerated at some point. And conversely, it must have decelerated a little bit in order to stop at the end. It's a little bit like that bench press. If you think about it, you can't move unless you accelerate a little bit. But I think the acceleration is kind of negligible at the beginning, at the end. So roughly, it's 100 newtons of friction force in the opposite direction to the 2 meters. So negative 200 joules of friction force. That's the idea here. So plus on it. So I do 200 joules of positive work. Friction does 200 joules of negative work. They cancel each other out. And nothing has changed about the box from one side of my office to the other. Zero net work. So have a great weekend. I will see you on Monday, same time, same place, and no more video overflow room.